to build the model, it's good to go look at the histogram again. So our suggestion looking at this histogram is that, although hardly perfect and hardly exact, we're going to approximate this histogram with a line segment that's horizontal, that's level. This histogram is somewhat uniform, not perfectly, but somewhat. So we're going to approximate these data with a line segment. It's very simple as density function goes. So let's start at, let's say 50, so because I think our lowest score is 55, and that should get us up to 100 here on this scale. So I'm going to go in increments of 5, label the x-axis the horizontal axis. All right, that worked. So these are test scores in points. And in fact, if we title this, these are really Geometry 1 final exam scores. So I'll just say Geometry Exam Model. That's what I'll call it. So I claim the lowest score is 55, so I'll put my lower boundary there for my line segment. The highest score is 100, so literally I'm just going to draw a simple line segment up to 100, and that's the density function. So I know this seems overly simple, but that's what makes this really so elegant. So our lowest score is at 55. The highest score is at 100. And this is a density function because all of the y values on this horizontal line, they're all positive. So we just have to choose the y scale in order to force the area under this density function between the function and the x-axis. So in other words, the area of this rectangle is what we want to force to be 1. So the area of the rectangle, that's just base times height. And I know the base extends from 55 to 100. So that base is 45 units long. So I just need to find the height that we would multiply by in order to get an area of 1. So if we divide by 45, we've got the height that we need. That's literally the y scale that we want to indicate here. So every y value here is at a height of 1 over 45. So literally, if you take 45, the base, times 1 over 45, the height, you get 1. And remember, the area under this curve is 1, which represents 100% of our data. So now areas under the density function can represent percentages of observations in our data set. We could even write the equation for this function. It's just y equals 1 over 45 for x values from 55 to 100. So literally, that's the equation of our density function, although it's more important to recognize how to use it, so let's use it right away. So let's estimate the percentage of students that earned some type of C or B on this exam using the density function. So C's and B's are in the 70s and 80s. So if you want to get technical, I suppose, a C starts at 69.5. That would round to 70. So I'll put that boundary at 69.5. And then I suppose 89.4 is the lowest B you can, rather the highest B you can get. 89.5 would round to 90. So I'll put this at 89.4. So the percentage of the data that represents C's and B's literally can be thought of as this area. The area of this rectangle under the density function. So our percentage is literally just that area, and our area can be found as the base times the height. So the length of this base is just the difference between the 89.4 and the 69.5. And the height of the density function, we've already indicated. It's 1 over 45. That's all we need to do. So if you go to your calculator, we'll go to the home screen, press second mode. So I'm going to take the 89.4, subtract the 69.5, and then I'm going to multiply by 1 over 45. That's the same as dividing by 45. So that gives me about 44%. So we'll round this to 0.44 or 44%. But we can actually use the data to find the actual answer. So if we go back to our data set, we can count how many C's and B's we had out of 28. So here they are. 1, 2, 3, 4, 5, 6, 7. Let's see here. 8, 9, 10, 11, 12, 13. 13 of the 28 scores were C's or B's. So there's the actual percentage. 13 out of 28. Let's take a look at what that is. Oops, clear that screen again. 13 divided by 28. And that's about 46%. So notice, the idea of a model is to approximate reality. And really, for this simple of a calculation for a model that's essentially just a rectangle, it does surprisingly well. So let's try another question, again using the logic of a density function. So on the back side here, let's estimate the percentage of students that passed the exam using the normal density function. Well, a passing score, if we go back to our model, a passing score would have to be higher than 65. I guess that's 64.5. So I'll put that boundary right here. Here's our 64.5, and I'm interested then in all of this area now. These are all of the passing scores. So the area of that rectangle then, its base is from 64.5 to 100, and its height again is 1 over 45. So this isn't a problem to calculate. So the area, literally the base is from 100, take away the 64.5, and the height is the 1 over 45 again. So we'll use our model to approximate this. 100 minus the 64.5. We'll divide by 45. That's the same as multiplying by 1 over 45. So it looks like about 79% passed if we round that. So this rounds to 0.79 or 79%. So let's see how close the model gets to reality. So using the data, let's find the actual percentage. So probably the easiest way to find the people that passed is to count the people that didn't pass. So let's see, there's 1, 2, 3, 4, 5 scores that are Fs, 5 out of 28. So that means 23 out of 28 are passing scores. So 23 out of 28, what's that? Let's find out. 23 divided by 28. That gives us about 82%. Again, the model isn't perfect, but that's not the idea. The model is simply an approximation to reality. So the percentages in our model are actually pretty close to what we get when we use the actual data. So in the last video then, we'll look at other ways to extend this model, how to find other values within the model, and also how to see that sometimes models aren't perfect, and that's okay.